use of class time. I want to get into this and talk about what is the best use. There's two things. When you have a region, called region 1 and region 2, region 1 will have parameters U1, epsilon 1, sigma 1. In general, we don't talk about sigma. It's lost. And we also talk about some beta 1 here and some beta 1. So you can assume for this case it's lossless. It's probably better. And here we're going to have a region with some U2, epsilon 2, Wilson sigma 0. And then you have eta 2, and you have the beta 2. And then the way Dr. Wentworth does it, a lot of people do this, they're going to draw a normal. Here's one region, here's another region. They're different materials. Typically, this is air. Usually we talk about a wave coming in from air, striking the ground, or striking a metal plate or something like that. Follow? But we're going to assume that this wave is coming in, and it's not normally incident. But the electric field for this case is going to be TE polarized. Transverse TE electric polarization. Now, I'm going through stuff that did last time. I'm going to go through it a bit quick just to show you, okay? So when we do this, this is considered the angle of incidence. And a wave is propagating in this direction. It's going to hit, some of it is going to scatter back like this. The E field will still have this polarization. The H field in this case will be polarized like this. This will be H incident. This would be E incident. There'll be a reflected field where the E will have E reflected here, and the H field will be in this direction, actually. And then there'll be a transmitted field, and there'll be a transmitted angle. And there'll be an electric field, E transmitted, and there'll be also a reflected field. A transmitted H field, pardon. This would be the transmitted H field. Now, I'm just going to put down this. Last time I showed you the electric field equations, then the magnetic field equations for both incident and reflected. I put them all on the board. Do you remember that? What we do when we find what's called a reflection and transmission coefficient, first I'll define it. When we're talking about the reflection coefficient, what we're doing is we use the same symbol. The technical term is gamma, and I want you to listen to this. This is really useful. What you do, did I hand back your quizzes? Mm-hmm. Okay, just making sure. And if you did it online, if you were, then I graded it and they should be available on, really, I believe they're on Canvas. They should be available on Canvas. Anything that you do that you load to Canvas, I'll grade there and it'll be right there for you to look, okay? And if you have questions, you can come and ask me. So for this one, you always start, now just think about the standard reflection coefficient. It's always the impedance you're going into minus the impedance you came from divided by the sum, right? Same here, you start with putting beta 2, beta 1, beta 2, beta 1. Here there's a minus sign, here there's a plus. Just showing you how I did it. Now, and this is in your book for the TE mode on. He doesn't actually have the symbol for the coefficient. Well, he does, but he doesn't do the ratio. It's equation 6.133 and 6.134. So now, here's the weird part. That's 82, but the angle, the cosine angle will be theta incident here. This will be cosine of theta transmitted. This is cosine of theta incident. And this is going to be, this will be plus N1 cosine of theta transmitted. The reason I do that, I always get N2 minus N1, N2 plus N1, and then the angles I put it. Y'all follow me? Now this is for TE. And can somebody just tell me briefly, how do you know a wave's TE? There's 2 or 3 ways. If in your own words, you don't have to use a formal definition. Anybody? Go ahead.
Isn't it if it's coming at a certain angle to the board or compared to?
Has no difference. Nothing to do with this.
If like so TE if the electric field
I'll make
is
it
like
easy. Let's
perfectly
go with Z.
projected onto the,
In a nutshell, if it's the plane of propagation that I'm looking at, the E field is perpendicular to that plane of propagation. That's one way. The second way is if it's TE, is the electric field is parallel to the boundary. There is no component that's not in the plane of the boundary. That's a TE wave. It's sticking out of the board. Like think of a perpendicular sticking out of the board that flies in it. That's the electric field. PM will be the opposite. The magnetic field will be transverse. This is TE. So that's the reflection coefficient. Make sense to everybody? We could do this and prove it. We could get the E field and H field at this boundary. That's where I was headed. And then set Z equal to 0 and take the ratio of E to H on this side, set it equal to the ratio of E to H on that side. And it will always be true. Brings up an interesting point. Then if you look at the tangent component of the E field on this side, it has both an incident and a reflected field, just like before for the normal incident, right? So you would have E incident plus E reflected. They would be aligned. They would be right, this and this reflected are in the plane. They would add together with any no cosine. That would be equal to the transmitted E field. You all agree? But the H field itself, you would have to get the projection in this direction. You have to get this one. So that will be reduced, all right? This is in the x-axis, the H field will be reduced by the cosine of this angle, which is this angle. I know this because I do it. It's got a minus sign there. The H field up here will have a cosine of this angle right here. Basically the same angle, cosine of this angle right here. But it'll have a positive. So you're going to have an H positive reflected cosine angle, H minus reflected, all right, down here. And that has to be equal to H transmitted. Now, I don't want to spend time on this because this is one of those proofs that people see and they say, and they don't have to repeat it. In physics, you'd have to be able to create that proof from scratch if you're taking 400 level course in physics, a book by Jackson or something. They always make you do these proofs. In electrical and computer engineering, I don't require you to do that proof. You have to appreciate how it's done. Find the transmitted and the actual reflected E and H field on both boundaries. You set the value of Z equal to 0 and you equate the field components. E tangent, H tangent, right? I mean, E on this side total, E on this side tangent, H total on this side, H. And then you take when you go ahead and you have that and you fuss around with it, because we know that E over H on this side for a propagating wave is eta, right? And E over H on this side is eta, correct, class? So then you can go ahead and you can solve. And this itself is the ratio, this is in the book, of E transmitted over H, over E incident, pardon me, E incident. Now that's important. That's the reflection coefficient, just as if we were dealing. I mean, this is basically just like normal, except now it's coming in manual. It's coming out in manual. The other thing we're going to talk about is E reflected over E incident. And that, now think about the transmission coefficient. What was it for normal incidence? Can anybody recall that? Anybody? Anybody? It's what? 2 A to 2 over A to 1 plus A to 2. That's one way to get it. What's another way to get it? Anyone?
1 month.
1 plus reflection. It works for this case. So this you can get. This is transmission. This is good. You know what? This should be reflected. This is reflected field. This is transient. Don't be afraid to yell at me. I kind of appreciate that. And this is what I do normally. I put a little thing perpendicular, and the symbol for this is transmission coefficient for purposes of science. Perpendicular way. You follow this? Everybody? So that's transmission right there, right here. And this would be equal to 2 times A to 2 cosine of theta incident over A to 2 cosine of theta incident plus A to 1 cosine of theta transmitted. Are you with me on that? Now, if you have your books and are looking, it's on page, these are on page 364. Take a look at that and confirm if you have your books. Let me see. I would suggest you make marks on your book and said, Baginski said this is TE and important. Something like that, so I tab my book, I don't have this tab, this is the second book I have, but any important information I need to go through, I literally tab the top pages with these little things. And I might even write something that says, these are Fresnel reflection coefficients for everybody, in case you see the word Fresnel and you're looking. But these are reflection coefficients. So that's transmission or reflection for a perpendicularly polarized wave, right? Now, if we had parallel polarized, just do this. I may do this one. I don't know. If I do it, the problem is it takes a good 15, 20 minutes to get this up on the board. And the students basically just want to know the equations, but I'll show you. Now we have a TM polarization. If this is region 1, this is region 2. I'm just going to say it's got beta 1 and beta 1. Forget the intrinsic parameters. This says eta 2, beta 2, right? Maybe I'll try to develop this a little more. Y'all with me? Now, again, what we do is we draw a normal. And just like Dr. Whitmer spoke, we call this Z. We call this X, so Y sticking out of the board. I think everybody can appreciate that. You all agree with that? It's right-hand coordinate system, so X cross Y, right, is the direction of propagation, or really a Z. Now, we'll put, let's say we have an incident wave here. This time, the H field is out of the board. So here, the H field is perpendicular. This is why it's called TM. And if I say E cross H is direction of propagation, that means the E field is this way in the plane of the board. This is E incident. We're going to have an angle just as before, theta incident. We're going to have a transmitted angle. And this is in your book, and it's also in the PowerPoint. If you don't want to write, if you open up the PowerPoints I gave you, you'll see this proof laid out bit by bit, with maybe even a little more information. Here, we're going to have a transmitted E field, and the H field is perpendicular. So it's H transmitted here. Then you're going to have a reflected wave. And here you're going to have the H field. The way he does it, there's two ways to do this, and I gotta be sure this book is consistent. Okay, yeah. Here's what he does. He's going to have the E field in this one, in this direction. That will be E reflected, and what he does for the H field is have it going into the board. So this will be H reflected. Y'all follow? Now the reason he does that, if you give me a second, remember if you take your right hand, use your index finger and put it in the direction of the E field's polarization. And then you take that, use your thumb as like an axle that you're going to hinge on, and then rotate it by small angle into the H field. So E cross H for a plane wave is the direction of propagation. Look up here. You got E, H has to be into the board in order to get a wave propagating this way. Y'all follow me? Guys, everybody? Now, I'm going to make a comment here. I'll prove it, but the incident angle is the reflected angle here. It always will be. For a plane, as long as these surfaces are planar. Mention one other thing, some of you may be looking on the internet. If you have, this is assuming you have mirror-like scattering, you have a perfect plane, the wave hits it, it's mirror-like, think of billiard balls and a pool table. The angle of incidence is the angle of reflection without English and all that stuff. That's the way it always works with electromagnetics too. Assume the regions are mirror in a sense. Right? Not quite true. When you have with a rough surfaces, you get what's called diffuse scattering. This is an advanced topic. But when you hit, the actual light beam will scatter. Some of it will come in all directions and will have a preferred lobe of scattering. That's diffuse scattering. That's like when light hits sand, all right, something like that. Now, some of you probably have seen light, when light hits a mirror, it reflects perfectly, right? That is coherent scattering, and there's other words for it, but diffuse and coherent scattering or mirror-like scattering are things that you have to be aware of. There are differences. For now, we're assuming mirror-like. Okay. All right, so now for this one, I'll just tell you what happened. The H field incident will have the ratio of, EI over the actual value, A/1, will give me the H field. Do you all agree with that, class? I can go ahead and I can say H incident will be, E naught incident over A/1. Now, when I take a look at this, the orientation of this thing right here is going to be in the AY direction. So I put that out here. Show you how we set this thing up. All right. Now this is going to propagate. So it will have E to the minus J beta 1, just as before. And C prime is actually equal to X times the sine of theta incident plus Z cosine theta incident. And that's what this just as before. Do you all remember I put that in there? Right? So if you take a look at this, the coefficient of X is really sine theta. And when you put Z prime in this, the coefficient of the X would be equal to sine theta incident times beta 1. Do you all follow me in this? And stop for a second and make a comment. This is important. One other thing that happens is, oftentimes in other books that are useful in electromagnetics, they don't use beta. What they'll use is the symbol K, which was equivalent to beta. They're both wave numbers, the radians per meter, the units. But then what they'll do is also give K a vector sense. I want to put this out here. So what they'll do is they'll take this information and they'll say that K here, vector here, will be equal to beta. Now that's, and then it'll have a unit vector in the direction of propagation. I don't want to spend time on this. I just want you to make you aware of it. Because no doubt some of you are looking on the internet, you're looking at Chegg, you're looking at all sorts of other resources, and you will see this oftentimes. Do you follow me? It is just like A and beta's magnitude are the same in the regions. The difference is sometimes they give K a vector sense. Just on that, okay? That's the only thing you need to know. Now, this is H incident right there. When we talk, yeah, that's it. We talk about H reflected. Here, it's going to be E not reflected over A/1, E to the minus J beta 1, and then I'll call this Z incident at, Z reflected at, where Z reflected as before is equal to X times cosine of sine theta. That won't change, but this will become minus Z cosine theta incident. And the reason for that is now it's propagating this way. You remember doing this last time? And then finally, the transmitted is just like this would be, this is going to be incident here. This is going to be reflected. The transmitted will be equal to X sine theta incident plus, X sine of theta transmitted plus Z cosine of theta transmitted. So first two incident angle, and this should be reflected, but I want to tell you the magnitude reflected in incident are the same. The angle is the same in magnitude. The transmitted angle is different. So that's the different values. This is H incident, H reflected, and H transmitted will look like this. It'll be E naught transmitted over, now it's A to 2, E to the minus J, and now it's beta 2, and now it's Z transmitted at. And all these are in the AY direction because this is the TM mode. Are you all following me on that, class? Let me erase this right here. I just want to finish one of these. It's going to be TM. Yeah.
So you have all of these going in the AY direction, but then in your drawing, it seems to me that it reflected is in the negative.
Yeah, you can put it negative.
So
That's,
either of those, can you use those, and then if you use the AY, you reflect that to go.
so
So if you were to use positive AY,
if you would assume the H field is in the positive direction, if you did that, then you would leave that alone. But here's the thing, when you did that, your definition of reflection coefficient would change in terms of a negative sign. Let me finish this and you'll see. The orientation, you know, I have the E field coming out of the board is positive. If I wanted to, I could have it going into the board, all right? That would be my positive, but everything else would have to follow suit, and the change would be felt everywhere. You're gonna see what I'm showing you will help you, I think. All right, so this is the H field. How do I get the E field for T? Let me get this out. Well, how did I get, you remember how I got the H field if I had TE for a point, what I did? Anybody?
You,
If you don't know, this is a good time to make sure you know. We're like a quiz. Let me say that again. We're like a quiz.
can you repeat the question?
I said, how would you get the E field if you knew the H? Now, I think you know, but just stop right now, right? Let me just show you the real way. You use those identities that I mean, those, I'll call them just formulas. They're truths for plane wave propagation. And one is that the H field itself in any region is really going to be given by the E field in that region, all right? Let me do this, actually. It's 1 over eta. These are phasor terms, 1 over eta in that region. Unit vector in the direction the wave is propagating crossed into E. I hope this is coming back. So this would be H field if you had E, correct? You can get the direction of propagation just by inspecting the wave, the Z prime. You can get that. You all with me? Either incident, reflected, or transmitted Z prime. Correct, class? All right. How do you get the E field if you know the H field? Something like that, but there's a minus sign, isn't there? Minus, and then there's an eta in the region, AP, right? Unit vector in the direction of propagation, crossed into H. These are in your book. I don't remember the page, but these are the two golden things you use for plane wave propagation. If you have one, you get the other, related to the incident reflected field or transmit. Y'all with me? I don't know where it is in the book. Somebody can find it if you want a page. Now, with me on this one. What I'm going to do, I need E, so I use this one. I'm going to do it here. Okay? So take a look at that. My H incident, right? H incident was equal to some, it's E naught incident over eta 1, right? And then it's going to be propagating e to the minus j beta 1 z incident path, right? It's in the AY direction. This is for the incident field. You agree with that? I admire people that take notes and do this like a scribe and have good handwriting. If somebody is just over the top good at this, let me know. I'll take pictures of your notes and provide it for the class. But I'm serious. It's taking notes is fine. All this is laid out in that PowerPoint I gave you. I don't know the exact point. It's fine. If I have that, now I want to get the H field, right? I mean, yeah, sorry, the E field. So if I want the E field incident, what do? I said it's minus, right? Eta in the region. In this case, it would be eta 1. Do you all agree with that? Then it's a unit vector in the direction of propagation crossed into the H field. Incident. Well, we got the H field. We got eta 1. It's an assumption. We need a unit vector in the direction of propagation. What is that? This would be for the incident wave. How do I get? Let me tell you.
Right. You just had to drop the X for AX.
Here's a simple thing to do. He's saying the right stuff. Instead of X there, put AX. Instead of Z there, put AZ. That's a unit vector. I can prove that if you want. It'll be intuitively obvious once you see this. Think of the extremes. Just do what I said. So it's going to be sine, huh? Sine theta incident AX plus cosine theta incident AZ. Correct, class? Y'all with me? Only thing I did is take the X, turn it into AX. Take the Z, turn it to AZ. This is easy. Now then investigate, see if you made a mistake. When I come in, the theta incident is 0. Isn't that normally incident? Y'all agree with that? So if that's normally incident, that means the unit vector should be just AZ, right? Agree? It should be just AZ. What happens when the angle goes to 0? When this goes away, sine of 0 is 0, cosine of 0 is 1, you get AZ, it works. That's my point. Said that. Y'all remember that? Do the other extreme. What if the angle is 90 degrees? Now it's zooming right up the x-axis, right? The unit vector would have to be AX. When it's 90, sine of 90 is 1, cosine of 90 is 0, 1 AX. Follow me? And therefore you can prove what I just said. Agreed, class? All right. Now, I have this. So I'm going to go ahead and say that E incident is equal to, you'll notice what happens when I take A to 1, and I'm looking at this thing as H, the 8 is canceled. So I get E naught incident, as I should. Right? Then I have a unit vector in the direction of propagation. I'm going to put it here. Sine theta incident AX, right? Plus cosine theta incident, right here. AZ. That's the unit vector. It's crossed into the H field. And I got rid of this term already, the front term. So it's crossed into AY times E to the minus J beta 1 times Z incident F. Y'all see what I'm doing? Yeah.
Is there supposed to be a negative sign? Or?
Yeah, there is. Usually when I write these down, I step back and look. I'll tell you one other thing I do. If you've had me, I usually circle negative signs because I'm prone to thinking I made a scratch on paper. I circle mine from this is a serious thing. That's make French sevens too, so I don't mistake them for twos. As you put a false below the stem. All right, now when you do this, I think you all can appreciate what I'm going to do next, right? Remember, this is for the incident field. What happens here? I get X cross Y is Z, correct, class? So I get that, and that means I get, I'm trying to make it all here. So this is going to have a coefficient of AZ, right? And then I get Z crossed, in this case, Y, right? Z crossed for Y is going to be minus X, correct? So this would be minus, and this would become AX. I'm doing it this way. Some of you may not like it, but I'm doing it this way to try to save space and time. Are you with me? And this is going to be minus, right? Hang on. Do y'all follow me what I've done? I took the cross product and just erased the vectors in there. I got rid of the cross so I can try to make this reasonable in length. Now, I'm going to do this now. You see that minus now? That will change these sides. This will become positive, and this will become minus. And lo and behold, that is the incident electric field. And for TM case, that's what he has at 6138 for the first, this is for incident field. Y'all see that, class? Page 366. That's the incident field. It's identical to his. I do it a little different. I don't keep rewriting that Z. I just define it up. I define the unit vector, and I got Z over there defined. I don't keep Z incident. Now, that's incident. I want to just tell you this. for transmitted, work with me here. The transmitted electric field will have the identical form as the incident. Because frankly, if you think about this, the actual orientation of H and E here is the same as the orientation of H and E here. Do y'all see that? It's identical. The difference is the angle, right? Can you all see that? So we know we're going to have a unit vector that's different. But with that exception, the angle is a little different. It has the same basic form as this. I'm going to just, I'm making this argument. I can just say this is E naught transmitted. And then you would have minus sine of theta transmitted AZ, this is correct. And then you would have plus cosine of theta transmitted times AX. Here, you would have E to the minus J beta 2 times Z transmitted. Reflected one's the different one. The reflected one, I want you to just remember. I just took literally what I did above for the incident field, and I've assumed you can make the change in your mind. If I went ahead and talked about transmitted E field beta 2 here, then the unit vector here would be the transmitted unit vector. Same exact form, only the sign would be of the angle of transmission, cosine of angle of transmission. You would turn the crank on this, the unit vector would of course be, it would have changed. And then when you would get identically that. And if you just replace it, this is what you'll get. If you look in your book, it's what he has for the transmitted fields. And that's 6.140. Now, if you go ahead and take a look at the reflected field, the only difference to the reflected field is we got the H field, right? Reflected. That's an assumption. When we go ahead, the unit vector now is what? The unit vector is going to be still sine of theta reflected AX, but then it's minus cosine of theta reflected AZ. Do y'all see it's going in the minus AZ direction? Are you with me? That would be how the unit vector would change. If we went and did this again for the reflected field, what we would get is two positives here. Take a look at your book if you have. You're going to get, because I'm running out of time with this, you're going to get E naught reflected, and then what you're going to get is two positives. You'll get sine of theta transmitted AX plus cosine of theta transmitted AZ. This would be AX, and it would be E to the minus J beta 1, and this would be Z reflected. Now remember, Z reflected is going to have a negative sign in the direction of propagation associated with the Z term, the cosine. With me on this? Did you have a question? See, this is, I am so sorry. I've had coffee. Now, to be frank about it, with the incident angle there, you say. We can prove that. That's how they prove Snell's law. All right, so now I've got the E field and I've got the H field. Here's the deal. What we do is we're going to say the E tan on one side is E tan on the other, H tan on one side is H tan on another, and we're going to go ahead and get the ratio of transmitted to incident and reflected incident. And I'm going to try to do this fast. Well, I'm going to try to do it in an efficient manner without a lot of unnecessary steps. So I'm going to do it here. You can look in your book, all this stuff I'm showing you. So what I'm going to do is now take E tan region 1 equated to E tan in region 2. When I do this, I want you to take a look at this. Take a look at the incident, reflected, and tangent. In region 1, you have incident, right? And you have reflection, correct? That's region 1. Everybody with me? All right. I need the tangent component. What would the tangent component of this be? Think of the drawing. Z goes that way, X goes, wouldn't it be the X component class? Right? If you're talking about the tangent E field, think about that boundary. Maybe I shouldn't have phrased it. This is region 1, 2. That's Z, that's X. Here's the boundary, right? When I take a look at the propagation, the E field itself is in this. If we wanted the tangent component of that E field, that would be the X component, wouldn't it, class? Can you see it? Are you good with that? I'm glad you're keeping me straight on this stuff. So the tangent component would be the X component, which would be this one, wouldn't it? So let's do that. We take E incident, E not incident. This is the incident part, times cosine theta incident. And here we're going to do one other thing. We're going to say, we're going to let Z equal 0 for this one. So I got the cosine of theta incident. And here we have to have, we have this term. We're going to add that to that. So it's going to be times, well, it'll be E to the minus J beta 1. And now when actually, when I make Z 0, if you take a look at this term, when Z is 0, this component goes away, doesn't it? For this X, the Z incident, Z hat prime incident, right? So this goes away, but I still have X sine theta. So I have X times sine of theta incident. It's that plus, then you get the reflective wave, right? I have E naught reflected. That's here. It's going to be cosine of theta reflected. Times E to the minus J beta 1. Now I need Z reflected, but I let Z be 0, so it's just X cosine of theta reflected. And that has to be equal to the transmitted E field's tangent component everywhere in that boundary for any X. So that means the tangent component there, the transmitted, would be this, which would be E naught transmitted times cosine of beta transmitted times E to the minus J here would be beta 2 times X. And here it's going to be times the cosine. So this is sine here, like that, sine. This is sine as well. Sine of beta transmitted. Now this is in his book. I forgot the page. I'm talking. He does this on 6.123 on page 363, but he does it for the TM mode. It's true for the TE mode. I've equated it. Now please watch this. This is real important. Okay. And this is, I'm not going to do a formal mathematical, we're going to reason it out. You all agree if X is equal to 0, and Z is 0, then you would get E naught incident cosine of theta incident plus E naught reflected cosine of theta reflected is equal to E naught transmitted cosine of theta transmitted. No, that if in fact X is 0, the exponential's argument goes to 0, does it? If X is 0, I got E to the 0, E to the 0, E to the 0. E to the 0 is 1. Agreed? Now, this is true always, is it? At the interface, correct, class? This has to be true. I want you to tell you something. Now, see these exponentials? It means that if this is true, I can literally solve for this in terms of the other two, put it in here, I can mess around with it, but I'm not going to right now. But I'm going to tell you, the only way this can be true for all values of X is if the argument of these exponentials is the same for all values of X. You all follow me? Just think to yourself, if you have 1 e to the j theta 1 equal to, say, 1 e to the j theta 2, The only possible way that can be true all the time is if theta 1 equals theta 2. Follow me on that? That's the argument here. So this is where we get Snell's law. So write this down. For Snell's law, have you all heard of it? I guess you figured this out, but I'm not sure if he's the first. Snell's law says that beta 1 here, right, times the sine of the incident angle is equal to beta 1 times the sine of the reflected angle is equal to beta 2 times the sine of the transmitted angle. I'm going to water that down a second. Now I got rid of the x's because they appear everywhere, and so do the j's, they cancel out. Agreed, class? Here's where it gets important. So when I take a look at this, take away this first part. Beta 1 sine theta incident equals beta 1 sine theta reflected. The only way that's true if theta reflected equals theta incident. Make sense? In fact, that's what I said before. Reflected and incident angle are the same. What also happens is beta 1 sine theta incident is beta 2 sine theta transmitted. That is Snell's law that you're used to when you had physics, but you didn't use beta, you used an index of refraction, didn't you? So, go over there and finish it. So this is how Snell's law really. Oh, but here, we're doing this for losses. There's a case, Snell's law for losses, but it's a little much. So now we talk about Snell's law, we really get beta 1, the sine of the incident angle. Remember, our incident angle is with respect to the normal. I was probably getting off normal. Is equal to this, you have to know. So Baginski says you got to know. Times sine of theta transmitted. Now, what is beta? Well, in general, beta is equal to omega square root of mu epsilon, isn't it? If it's lost. Everybody? Take a look here. If I put omega square root of mu 1 epsilon 1 is equal over here, and I put omega square root of mu 2 epsilon 2 here, the omegas cancel. Can you all see that? They will cancel. And what you're left with is square root of mu 1 times epsilon 1 is equal to square root of mu 2 epsilon 2. We're going to make it even easier. If I take a look at this, this is really equal to omega square root of mu naught epsilon naught square root of mu relative epsilon naught. You want to hear that? I factored out the mu naught epsilon. You see how when I put beta 1 here with this, and you put right here mu relative 1, epsilon relative 1, and equate it here with this, only mu relative 2, epsilon relative 2, the omega and square root of mu naught epsilon cancels. Okay? On both sides. So you're left with this. You're left with square root of mu relative 1, epsilon relative 1, times the sine of theta incident is equal to the square root of mu relative 2, epsilon relative 2, times the sine of theta transmitted. It's getting a little tight right here. And here's what we usually do. We usually assume non-magnetic regions. And that means mu relative is equal to 1. So you're left with this. Square root of epsilon relative 1 times the sine of the incident angle is equal to square root of epsilon relative 2 times the sine of the reflected angle. And you want to take a guess what the square root of epsilon relative is termed in general? Anybody know? I bet you do. Yeah, do you remember this from physics? You had this? This is a very standard thing. You had to know this in order to pass your physics. Of course, you know, like chem F equals ma kind of deal. That's the same thing here. This is that important. So normally what you did is you didn't write in terms of square root of epsilon. You put what's called the index of refraction. And that is not a script. That's a normal n. Which is hard to write differently than scripting. That's why I tell you it's the index of refraction. This is good enough. But if you want, you can replace that with N1, index of refraction, times the sine of theta incident is equal to N2 times the sine of theta distributed. Transmitted, transmitted, my gosh, right here. And typically you do this. They'll divide by N1. N1 for air is 1. And really you'll get theta incident here will be equal to sine minus 1 of N2 over N1 times sine of theta transmitted. That would be the incident angle. By the same token, if you wanted the transmitted angle, that's what you're usually after. I'm going to reverse these. Then you would have eta 1 over eta 2, or N1 over N2. And this will become theta transmitted. And this will become theta incident. Can somebody tell me where that is in the book? And this is the Snell's rule. Sorry, this is incident. And this is typically this is the way it's done. You'll have something about Snell's law in here. You still have to get the reflection coefficients. 63.
Still has the beta values, but
Yeah, I like doing it in terms of the intrinsic impedance because that's Snell's law, usually how it's used. Let's finish this up here. So this is the continuum of incident and equals reflected. That's for the E field, right? Let me just finish this up. I'm going to assume that we're going to let Z equal 0. We get that. You all follow me? That's the tangent components. Let me finish this. With me? Now we get the tangent E field. So we say H incident, right? Which is tangent, which is E naught incident over theta 1 plus reflected E naught reflected over, oh, I'm sorry, the reflected word has got a negative sign, so it's minus that equals E naught transmitted over theta 2. The H field is tangent already, right? For the TM mode, it's transverse magnetic, so it's tangent to the boundary. With me? So I just set the exponentials to 0, right, for the incident and incident, reflected, and tangent. These exponentials go away, and you add them up. The reflected does have a negative sign there. Make that a little more clear. Now, those are A's, not B's. Okay, now, here's the deal. We want to get the ratio of E incident, E reflected to E incident, right? So we take this one and we divide everything by E incident. You with me? Both sides. What happens is this goes to 1. Reflected over incident would be equal to the reflection coefficient, right? And then this would be the transmission coefficient. I hope you can appreciate. I'm trying to save you some time here. So this would be the transmission coefficient for the TM wave. I'm just dividing everything by E naught incident. E naught incident over, E naught reflected over E naught incident is the definition of the reflection coefficient. E naught transmit over E naught incident is the definition of the transmission coefficient. With me? Are you with me on this? Sorry. So now I do the same up here. And that goes to 1. This becomes reflection coefficient. And this becomes the transmission coefficient. Now, most of you can guess what I'm up to. If I want to solve for the reflection coefficient, listen to me now. What I'll do is solve for the transmission coefficient from that equation and plug it in here. You all see this? And then I'll have an equation with just the just the reflection coefficient. Do you all follow? How many understand what I'm up to? You with me? So I'm gonna do it over here. So now I have, this is one, that's equal to 1/8 of 2. And now I solve for the transmission coefficient, so it's reflection coefficient Tm, this times cosine of theta reflected plus cosine of theta incident here. And I gotta divide this whole thing by cosine of theta transmitted. This is getting interesting. And now I have this equated to that right there. And I have to do, after that, I need to do some multiplying by etas. You're gonna have to forgive me for this. And you do all this stuff and turn the crank on it. Yeah, when you do this, you're going to get the reflection and transmission coefficients. I'll look over by 1 minute to get that done. And if you look on page 367 in your book, I'm sorry, I'll just put up the equation I just put down there is what he has in 6.141, but I want to tell you one thing. What I didn't do, I didn't get rid of this term, and I didn't go ahead and group everything, but what you're going to get, and let me put it over here, will be the reflection. You can look in your book, and the transmission coefficients. Just bear with me. I'm trying to get this thing done without flying through it. Probably feel a little, maybe not overwhelmed, but you get tired of some of cosines of you. So here's what actually happens, and here's how I think sometimes the professor tells him how he thinks that it helps a lot more than just raw facts. So here's how I think about it. Now this is for TM. Right away, I start with the reflection coefficient of the surface. I always go ahead and put eta 2, eta 1, eta 2, eta 1. I know on top, if it's normal incidence, I'm going to have a minus and a plus. You with me? That's what now I know before that was cosine of theta incidence. Here, if you look at a book, it's going to be cosine of theta transmit. Go ahead and take a look. This is going to be cosine of theta incident. This is going to be cosine theta transmitted. And the plus sign here is going to be cosine of theta incident. Now, if you can look in your book, that's what he has right next to E naught incident equation 6.141 on 367. Do you all see that? That's the I reason. The second part was a little tricky. The transmission coefficient, we put Tm here, is not equal to, or is unequal to 1 plus the reflection coefficient for Tm. It is not. You can use that, but you have to multiply by something. What's actually equal to, and here's what I always do. I know I have 2, eta 2 will always appear. I have eta 1 and eta 2 downstairs with a plus, right? And here, you'll see in this book, this is going to have the incident angle. And if you look a little further down, below there, you're going to see that that's eta 2 up top. Eta 1 has the incident angle for cosine. So these are kind of warnings. If you would just do, the standard diligence as we did before, you would take twice this value value over the sum. That's how you do it for TE. But for TM, it's not twice that value. Right? Well, it's twice what? It's 8 to 2, all right? But it's incident here. Take a look in the book. And then this is going to have incident 8 to 1. This is transmitted 8 to 2. All follow me? So there's different. But what this allows you to do, and I'm over by 5 minutes, okay, about 5 minutes. I got to stop it. Here's the beautiful thing about this. For TM modes, you get an angle where you get total transmission. The reflection coefficient goes to 0. You don't for TE modes. I got to show this to you. It's called Brewster's angle. How many have heard of Brewster's angle? All right, and it's a very beneficial effect. It means all the TM wave will get in and no T or very little TE wave. I've got to give you some homework related to that. I'm sorry, this always takes a long time. To make sense. Did this help at all for you understand? All this discussion, I know. Some of this stuff, if I'm where you are, I probably wish the professor went a little faster and just wrote the equations down to solve problems. I'll give you some problems to solve. And especially that one that I thought was up there, I want you to go through that. And what we do with any wave into a boundary, we decompose it into perpendicular and parallel components. And then we calculate the reflection coefficients for each to get the total reflector, the transmission coefficients for each. Then we get the transmitted electric field. So we take the incident parallel or TM components multiplied by the TM transmission coefficient to get the transmitted field. Take the incident perpendicular components multiplied by the perpendicular transmission coefficient to get the transmitted fields. With power, last thing I want to say, power normal to the surface. If you know what the power flow is, incident reflected. If you take those two and take the component of each normal to the surface, that will equal to the power flow in the other region normal to the surface, even though the angles that they're traveling will be different, but it's always normal in the Z direction. I'll leave it. Thank you for hanging out. Sorry. I'm debating. I'll send you something by 5 that make it problem. We haven't looked at the COVID-19 update yet for Auburn area. I don't know if it's going to get really hard.